Hello everyone. Good morning. Sorry, good afternoon. Uh, I will wait for 1 or 2 minutes to join others. Hello everyone. Good morning. Sorry, good afternoon. I will wait for 1 or 2 minutes to join others. Hello everyone. Good morning. Hello all. Hello friends. Yeah. First of all, thanks to join participants for the automotive application for CAN protocol webinar. And I would like to thank JKK Nataraj College of Engineering and Technology, the Department of ECE, and I would like to thanks HOD and coordinator Mr. Sindhil and yes, then Lakshmi. Uh, I think we can go to the topic now. Yes, uh, control area network for automotive application. Okay, before going entering to the complete CAN protocol, we have to look into why this CAN protocol is required and why it's coming to the picture. And yeah, what are the things where uh, properties were there in the ECU system or automotive system. Once we see these details, then we'll come to know why the CAN protocol and the LIN and the FluxRay, those kind of automotive protocols are required. We'll get some idea. Then we'll see complete CAN protocol overview and CAN protocol frames and how the bit stuffing and bit streaming, those details. Yeah, first of all, we'll enter to uh, there was a question how many ECUs were used in a car? ECUs electronics control unit. Uh, if you see in 2016 in a luxury car, it's almost 150 ECUs were used in a car. Uh, Even if you see the 2015 survey, there was a 80 ECUs were used. Of course, if you are having small size of car, then it would be a very handful or very less number of ECUs were used, more, not more than 10 or less than it. Yeah, where is the motivation? Development of CAN is came. Um, when when you are using more and more of electronics in modern motor vehicles, you will get the complex system. Like if you are for a car has a multiple functionalities like a airbag, braking system, ABS system, and engine management system, powertrain system. These kind of lot of ECUs. I mean the electronic control units were used in a car. So these has to be communicated to each other. Like powertrain system will communicate to engine management system, and uh, yeah, braking system will communicate to airbags. Yeah, these kind of communication will happen each and every uh, cars. So to communicate with different ECUs or exchanging data between various ECU, we need a protocol system or we need a standard form or we need a bus. That's why we are going for CAN. We have a lot of advantage over the CAN that we are coming to later. If you see here, we have a engine control system in a car, anti-lock braking system, and body electronics, and airbags, transmission control. Yeah, these all are individual ECUs were used in a car. I think you got a picture like why the ECUs were used in the car and how it's communicated between each other. Those details. Yeah, if you uh, do the point-to-point communication from a ECU, like if you are giving some data from engine control to airbags, then it would be much complicated. If you see the disadvantages, the system will be bulky. You'll if you see just imagine the connections, it will be bulky. A lot of wires involved on the different ECUs and multiple sensors will be available on the cars, and it's very complex to maintain. If something error comes, then we cannot predict or we cannot uh, diagnostics. It's very complex and it's difficult to install. I mean the installation or connection, making the connection, it's a very difficult and it's unreliable. Yeah, if you go to the conventional network like a yeah, it's a serial bus communication. If you already I have mentioned, if you go for point to point interconnection, then it will be a more material cost and a more protection time, and it's a difficult to maintain. And now or some 50-40 years back, Robert Boss came up with a solution with a serial bus communication for CAN. It's a CAN is a serial bus communication. If you see here, the all the ECUs are connected with one single network. So the exchanging of ECU 1 to 2 or 1 to 5, it will be very easy. The connections are the yeah, physical connection. If you think the physical connection, it will be very easy. You can directly connect two wires. CAN has a two CAN high and CAN low, two wires which is connected on the network bus. So the connection wise it will be very easy. That's the main advantage for CAN and even other lin kind of protocols. Okay, if you see, as already I have mentioned, adapting bus communication instead of point-to-point communication. Yes. Uh, then transmit receiving information through the bus, not for the individual ECUs. It's a throughout the bus, the information will be available. Whichever uh, ECUs required those information, that ECU will take in the data from the bus. Can it's advanced serial bus protocol that effectively supports a distributed control system. It's kind of not a master slave thing. It's a distributed control system. It's a multi-master, you can say. Any network can initiate the communication based on the CAN priority. I mean the CAN ID, message ID priority. Okay, the next one is components in serial bus communication. Yeah, the first one is interaction layer. The next one is bus access, addressing, data protection, and synchronization, topology, physical layer. Uh, we are going to detailedly see these details. First, interaction structure. There will be a multi-master interaction, master-slave interaction, time-triggered interaction. The multi-master is each node can have a equal priority to transmit the data into the bus. Based on our design or our logical, we can transmit any data from any node. Here the node means kind of ECU or sensor. It's a the next one is master slave. A special bus will be act as a master. The other nodes like a sensors, those things act as a slave. This is kind of a master slave communication. Whenever there is a request from master, slave will transmit the data to master. Its lin protocol will act like this. The next one is time triggered. Bus access is divided into number of time slots among nodes. Then a node have access to bus only its scheduled time slots. If you see the FluxRay communication, FluxRay is a time triggered protocol. The every dynamic or static frames will have a data. Once the time triggered is over, then you will won't get the updated one. The next time triggered only you will get the data. Okay, the simple example is multi-master is scan and a master slave is lin protocol and a time triggered is FluxRay. Next one is topology. There will be a multiple topology. Uh, the first one is star topology and the next one is bus system. Already we have mentioned can is under the bus system and the ring which will be connected all the ECUs kind of point to point communication, the star and the ring topology. But the bus topology will be we have a common shared bus. All the ECUs or sensors will be connected on the shared bus access. Controlled bus access. The right to bus access is predetermined before bus access. Yeah, like a lin. It's a centralized method where the single node control the bus can be accessed. The next one is the decentralized method and demand-based data exchange. It's demand-based data exchange is whenever there is a requirement, then only the data exchange is possible. But in the controlled bus access, it's not possible. The next one is stick bus access. The bus access is not a predetermined and it's completely run on the desired runtime. Whenever there is a runtime data change or whenever there is a ECU changes, the data will be transmitted. The example of this one is carrier sends multiple access with a collision. The next one is addressing. We have a two addressing types. One is sender selective, the next one is receiver selective. Each node will be assigned unique node address. This is sender selective. Sender will be identified and decide receiver by sending nodes data. Here the special addressing is required to multicasting or broadcasting thing. And the next one is receiver selective. Here the receiver identifies the desired message based on the frame data received. Like whenever you are receiving a data, based on that you are initiating the next transmission or next interaction or next information exchange. Here there is no need to assign a node selection or node addressing. Synchronization. Uh, there is a two type of synchronization. It's a one is asynchronous transmission and a synchronous transmission. Synchronous exists during the transmission just a few bits with the start of and stop pulse. For longer data blocks, sender must be synchronized receiver with start and stop pulse. Synchronous transmission is mainly based on the clock frequency. There is a synchronous clock frequency will be transmitted. Based on that, the data will be or data bits will be transmitted via bus. Okay. Yeah. Physical transmission is asymmetric and symmetric and optical. Maybe I will go a little bit faster because we are going a little bit. The components used in the CAN protocols are topology is bus topology. Already we have seen the interaction layer is multi-master and bus access is CSMA CAA and addressing is a receiver selective addressing. Synchronization is synchronous transmission. It's a clock based transmission and the physical transmission is twisted two wire pair symmetric transmission. Okay, these are the parameters we are going to see now. First of all, we will go to see the introduction to CAN. What's the CAN and those details and characteristics. What are the characteristics available in the CAN and frame formats and frame types. What are the frame types available or in the CAN protocol and frame how the frame formats is there. The next one is message accepting filter and message validation and CAN error handling, bus synchronization and bit construction, how it's dealt in the CAN protocol. Maybe we'll go first. CAN history. CAN is developed by Robert Bosch in mid of 1980. It's a revolution of automotive application. If you see the previous serial bus communications like SPI, I2C, you have a lot of complex over there because you cannot use the uh, multi-master concept. It's very difficult to maintain those kind of serial communications, but can bring the solution. It has a bus system and it has a multi-master capability, so it bring the more reliable, safer, and secure data communication in the automobile system, and it's a more fuel efficient cause or came after CAN protocol. Okay, it's a CAN is a control area network. It's a serial protocol already I have mentioned, which which is supports real time. Embedded system of complete embedded system is real time system. You have uh, it has a yeah, you can imagine it's a real time means if you apply brake, then immediately the wheels speed should reduce or the wheels revolution should bring to zero. That's the main thing in the embedded system or real-time system. That will be achieved in the CAN protocol, and it's a very high level security has. And the CAN is a serial bus system, especially shoots for networking intelligent device as well as sensors. Those things involved ECUs, those things involved in the CAN protocols. CAN is classified as a class C in vehicle network. I mean SAE, Society of Automotive Engineering and Classification, they're defined as a class C, and it's a high speed capable. And the main advantage is the latency time is very less. Can support bitrate up to 1 Mbps. Yeah, now CAN FD is available, and even the recent time we have a CAN XL. It's a new protocol, is upcoming protocol, and yeah, almost currently automotive Ethernet is ruling the automobile industry, but still CAN is a highly used protocol in the automotive industry. How the CAN node will be looks like? There will be a sensor actuators, and multiple sensors will be there, and these inputs will bring onto the microcontrollers. This is a microcontroller. Simply, if you see, we have a admal controller and a microchip. We have a microcontrollers which will be interact or physically connected, or there will be a two possibilities: inbuilt CAN controller, I mean inbuilt CAN transceiver, or outside. If you see, uh, like you have a ADC sensors input. Once the ADC is received to microcontroller, that will be transmit to CAN controller. Its CAN controller is it will transmit how the CAN frame format will be there. That way, microcontroller will give only the data part. Maybe once the frame section is we are going, that time it will be clear. Then from CAN controller to CAN transceiver. This transceiver will transmit or converts the CAN controller format to physical bus format. I mean the CAN low, CAN high, 0 to 1. And here it's a serial communication CAN TXT or XT. I mean CAN transmission and receiver will be data format will be there here. The next one is characteristics of CAN. Uh, yeah, we have a main advantages CAN prioritization. Here, based on the CAN identifier, CAN prioritization of the messages will be possible. That is the main advantage of CAN, because if you are fuel is for example, in a car, you have a lot of issues like a mm, braking system and a fuel system, like a music system. If music is playing, if you are applying the brake, definitely music should be make it as low priority, and the brake should have a higher priority. Then only the braking will be applied immediately within a fraction of microseconds. That's the reason CAN has a prioritization concept in his own. Whenever there will be a braking system, then the CAN ID or CAN ID of braking system will be higher compared to the music system. That's the way of designing in the CAN. Here the configuration flexibility. Here there is no theoretical limitation of nodes, but practically we have a lot of limitation in a car. We cannot offer more number of nodes, and but theoretically there is no limitation over. Then multi-master concept, uh, the broadcast communication also possible. Multicast reception with time synchronized way of communication can. And the main advantage is error detection and signaling. You can detect the error and retransmit your data to the bus. That's also possible in the CAN. And automatic retransmission and for the corrupted message. If there is a message corrupted because of some physical interruption, then the CAN message will be transmitted automatically because you will get a error signal back to the CAN. Then you comes to know there will be a error, then CAN will be taken care to retransmit the data again. Distraction between temporary error and permanent failure of the nodes. Okay, now there will be a distinction between permanent error or a temporary failure. If there is a temporary failure, then the data will be transmitted again. Then it's a permanent failure, then bus will be going off. The power, like battery operates sometimes with, if you are not starting the car, then it will be operates on the battery, so the controllers will go to the sleep mode. That possible, those kind of intelligence has a CAN controller or CAN protocol. Each CAN message can transmit 0 to 8 bytes for user information. Like if you want to transmit one sensor data with 8 bytes data, that's possible. Even 1 byte, it's possible. It's like a 0 to 8 bytes. Any number of data you can transmit on a message. In a single message, you can transmit 0 to 8 bytes. The main advantage of CAN-FD is increasing the l- length of the bytes. It's a 0 to 64 CAN-FD. CAN, message-based communication. It's a, not a address-based communication. It's a mainly for message-based communication. It has a lower weight and size and installation cost. Mainly the installation cost. That's the reason CAN will be rolling almost 1918 means almost it's a, now it's a 40 years. Still 40 years CAN is rolling the automotive industry. That's the main advantage. Application layer, layered structure, layered structure of CAN node. Application layer, object layer, transfer layer, physical layer. Totally we have a 4 layers. Here the object layer, okay, we are going to see detailed things, but still application layer is like uh, we have a complete system, but still we have to see what frames are going in the bus. Then only we can diagnostics, or during initial development we need to see. That's that time we have a application layer involved on the CAN nodes. Object layer, it's a message filtering, message and status handling. It's like a, if you want to receive only particular messages on the CAN side, that will be possible on the object layer side. And the transfer layer, the fault and error detection, signaling, message validation, acknowledgement, arbitration. Arbitration is the main concept. Will come. We are going to see upcoming slides. And message framing, transfer rate and timing. Those details will be, those things will be handled on the transfer layer. And the physical layer, it's a bus, exactly on the bus. That is signal level and bit representation and transmission medium. This is the main thing, like you are connecting the CAN high low, that will be coming under the physical layer. Yeah, if you see here, CAN is a insensitive to electromagnetic okay, there is a EMI inference, then CAN will be insensitive. There will be no problem. If EMI hits on the bus, both the bus line will affect on the same way, which leaves the differential signal unaffected. Okay, if you see here, this is the CAN bus. Here CAN high, CAN low. The each ECU nodes or each node has a two line CAN high, CAN low. Similar things. If you shielding the bus will be giving the more improvements from the EMI hits. The next one is bus characteristics of CAN. Okay, if you see here, this is the main physical layer uh, concept. There are two logic states. One is dominant bit and another one is recessive bit. You have to remember always the dominant and the recessive bit. This will be the main concept on the CAN physical layer. The dominant bit is logic level 0 and the recessive bit is logic level 1. Okay, if you see here, there will be a truth table. If you consider there will be a three nodes connected on a CAN bus and how it's reacting based on the bits. If all three nodes are in dominant bit, the bus end of the bus or bus state, the complete bus state will be dominant. I mean the logic 0. Even if there will be a one bus in the recessive, I mean logic level 1, still the bus state will be dominant. The logic level will be 0. This is the arbitration concept. This is very important in the CAN protocol. Here the prioritization will be coming to the picture. Whenever there is a dominant bit on the bus from the node, then the bus will be automatically turned to dominant bit. That node, first dominant bit transmitted node, will win the bus. We'll see the detailed things in the upcoming slide. If you just remember, the dominant bit is logic level 0 and recessive bit is logic level 1. The dominant bit always wins the recessive bit. This is the main thing. Yeah. Now coming to the bit arbitration mechanism. First, you are transmitting, for example, here three nodes are connected in a bus. In a CAN bus, this is the CAN bus. If you see the laser mark, this is the CAN bus. And these all are three nodes connected on the same bus. And this is the frame, CAN frame format. This detailed things we are going to see in the next one. Arbitration. Why CAN has a arbitration? As already I have mentioned, CAN has a prioritization technique. If you want to make like a braking system has a higher priority, then you have to assign lower CAN identifier. The CAN identifier values should be low. Then you will get higher priority on the CAN bus. Like CAN 1 will be CAN 1, sorry, CAN 1 or node 1 will be assigned 0 and CAN 2 assigned to 1 and CAN 3 assigned to 3 means then CAN node 1 will has a higher priority. But here the different case, for example, I'm saying the start of the frame. Initially, when if you, for example, all three CAN nodes transmitting data at the same time, if this is happening on the CAN bus, just think if that will collapse the complete bus if there is no arbitration concept is there. Because if multiple nodes are connected on the same bus, if multiple nodes transmit the data on the same time, then collapse the data will be collapsed if there is no arbitration concept. But luckily can have a arbitration concept. So even if all the nodes are transmitted on the same time, Based on the priority, the arbitration will be involved on the CAN side. Then the bus or CAN node will win. Only one node will win the bus, occupy the bus. Start of the frame will be the common one, so the bus level will be the same. Then already I have mentioned these all are the recessive bit. All three nodes has two recessive bits and two dominant bit, and again sixth bit is recessive bit here, here, and here. Next, if you go the fifth bit, dominant bit, recessive bit, dominant bit. If you see the node 2 is a lower priority, so this won't win the bus. Then if you go to the node 4, recessive bit, and then recessive bit. If you go to the bit 2, here also recessive bit, but here it's a dominant bit. So node 3 will win the bus. Then node 3 data only transmitted on the CAN bus. I mean the other nodes will receive node 3 data. Then once node 3 communication is over, then node 1 data will be transmitted, then node 2 data will be transmitted. This is the main advantage of arbitration. I think you will get the complete picture how the arbitration is working and the CAN transmission is working. Okay, now we are going to see the frame formats. We have two frame formats. One is standard frame, the next one is extended frames. Standard frame has a 11-bit identifiers. Extended frame has a 29-bit identifiers, but still standard frame has a 8-bit of 0 to 8 bytes of data, and the extended frame also 0 to 8 byte of data. Why the extended frames are coming? The standard frame means how many nodes you can, or how many messages ID you can create. The 2 power 11 only. That's the limitation. But if you go to the extended frame, then it's a 2 power 29. Huge number. That's the reason extended frame is coming to the picture. Then frame types, uh, data frame, remote frame, error frame, overloaded frame. Totally 4 number of frames, different frames are available in the CAN protocol. Data frame. CAN message structure is, if you see how the message frame, data frame will be there. First is start of the frame, next is identifier, CAN identifier, and control signals, and the data, CRC, acknowledgement, end of the frame, then interframe space. Start of the frame. It's a For the start of the frame, it's a single dominant bit. Already I have shown you. This is the start of the frame. Just a single bit which starts from dominant. That is start of the frame. The next one is identifier. 11-bit identifier has a 11 bits, and one is remote frame transmission request. The next bit is, if it's a 29-bit identifier, then it's a yeah 0 to 28 bits were there, and it has a SRR and identifier extension, and again RTR, remote frame remote transmission request. It's a remote transmission request is mainly for the uh, if one of the node is required the data, then with a 0 data byte with the zero data, this data with the zero data, it will transmit one message with enabled of RTR, remote transmission request. Then with respective node will transmit the message from their sensors. Those value will be taken to the expected node. That's the main usage of RTR. Control IDE is a, already I have mentioned that, and R0 it's a reserved one, and data length code. How much data you are transmitting for 8-bit. If you are transmitting zero data, this data part, how much data you are transmitting, going to transmit, that will be given in this bit stage. If you are transmitting 0 bit, then 000, then 1 bit 0010, like that. It goes to up to 8. Then R0, R1 were reserved for the future purpose. Okay, these things are bits, single bit. It's not a byte, single bit how it's transmitted. These all the things are single bits. Then the data field, there will be a uh, 9 chances of data field. One is 0, 0 it starts from 0 and ended with 8. You can start or based on the requirement or based on your data on the real time or runtime, that will be transmit to the other nodes. CRC, it's mainly the main advantage of CAN thing is CRC also. You are transmitting on data from a node. The data will be received from the other node B. How to ensure whichever data node is transmitted and the node B received data is same? How to ensure? Here the main picture is CRC. Here we have a CRC data which will calculated on the node A, and that will be evaluated on the node B, so that we can verify the data will be whichever received on the node B will be same as a node A. There we can say the both the data will be whichever transmitted, the same will be received on the node B. Here, to ensure the data transmission is successful, CRC is required. The next one is CAN acknowledgement. This is mainly for the to ensure that the current frame is completely transmitted on the bus. For example, node A transmitted some of the net data, and node B is not interested those data, but node C is interested on the data. Then node C, once the data is received, then it will acknowledge it. I have received the data, all the datas. Then the node A is comes to know the data will be acknowledged, so data will be received on node C. Then this is main some status were there. You can go through these details how the strategy is working on the acknowledgement part. If there is a error, then it will be repeated, or it's again go to the start of the frame. Okay, the end of the frame, it's a 7 recursive bit continuously. If you transmit that the end of frame, it will be transmitted. Then interframe, it's a again 3 recursive bit transmitted in interframe. Interframe space is like a one frame is transmitted, then bus need a little gap or little bit gap to identify the next frame. That is called interframe space. Okay, already I have mentioned this is the dominant bit and recursive bit, how the bus resulting. If uh, two recursive bit, then bus state will be recursive. If either one node or one of the node has a dominant bit, then bus will be always dominant. Okay, what is the standard data frame and extended data frame format? How is the frame format? Start of the frame already I have mentioned. 11-bit identifier, remote re transmission request, IDE and reserved, DLC, how many bytes were transmitted, and CRC field like that. The extended frame data frame is nothing like, it's the same. Start of the frame, again 11-bit identifier. Instead of RTR, here we are using SCR and ID is same. Then we are saying here SRR, we are saying it's an extended frame format. So again we are transmitting 18-bit identifier. This this is identifier, message identifier, and this is message identifier. I think you got. For us, we have a name. Like everyone has a name. That is called our identity. Same way, this complete frame has a identifier, identity that will be assigned here. This is 11-bit identifier. Here 29-bit identifier. This is same. Okay, then remote frame format. Already I have mentioned it's a that there is a no data part over here. It's a DLC is always 0. It's mainly getting data from the other node. Error frame format. Okay, we have multiple errors like a active error and a passive error in a CAN protocol. It's like a 6 dominant continuous bits will be active error, or 6 continuous recessive bit will be passive error. Okay, why 6 is coming to the picture? I will say there will be a bit stuffing concept will be there in the CAN. That will be coming to the next. Okay, the overloaded frame, if you are loaded one frame already, then you are trying to load again the same frame, then there will be a collision will happen. That will be detected on the CAN frame and reported to the microcontroller. The microcontroller will react based on that, and you should take your design as well. Okay, the interframe space already I have mentioned, it's a 3-bit interframe interframe space is required. We have a message accepting filters. Already I have mentioned it's a kind of if you want to accept only few of the frames, then you can set the filters. All already initially I have told all the nodes has received all the frames. If you are transmitting one frame on the bus, then all the nodes will receive this all the frames. But whichever node is required that data, only those nodes will process the data. Remaining all the other nodes will ignore those messages. For that you can still you can set the filters, and the message acceptance filter will be set like this. Uh, Here transmitter of ABS will be talk, it will be sent, and AC and EMC ECUs were has a mask like a filtering concept. Based on our identifier, the mask filtering concept will be defined in the ECUs. The AC ECU doesn't want these ABS data, then there will be a mask, then that will those data will be directly rejected on the CAN transmitter itself. ECM is required those data, then it will allow all the data from ABS, then the data will be processed on the ECU level. Message validation for transmitter, the message is valid, and if there is no error until the end of the frame, then the message is successful. For receiver, the message is valid if there is no error until last but one bit of the end of the frame. Type of error, if there is a error coming on during the validation. If there is a CRC error, I mean already I have mentioned to validate the data whichever transmitter. then it will be reported as CRC error. If acknowledgement is not there, any of the node, then it's acknowledgement error, form error, bit error, stuff error. Stuffing is a concept to involved in the CAN protocol that we are going to see now. Error handling. Okay, it's a simple thing to know how the CAN bus error handling is happening. uh, Bus will be in the error passive state, then this will be going to off state, bus off state, then reinitialization is required, then bus will go to the active state. If something is happening to going to passive state, then again it goes to or if it is a sleep mode, directly it will come to the active state. That's possible. Message coding. Okay, here we have a message coding. It's a non-return to zero coding. Keep the frequency of the signal on the bus is minimum. That's the main thing. The next one is bit stuffing. This is the main concept in the CAN, or one of the concept. It's not a main concept, but it's one of the concept in the CAN. But it's a new for not completely used for other protocols, but only CAN it's used, and even some of the other protocols also. If you see here, data will be just if you imagine data will be transmitted like start of the frame and 10 bit of identifiers and control bits, data bits, and the data byte. If you transmit like one dominant bit and complete 10 recessive bit, if you see 1 1 1 1 1 1 means it's almost ff, sorry, 7ff, then this will be not same as like in the bus. Why? Because uh, to ensure the sufficient recessive and dominant edge to ring synchronous, the synchronization technology is involved here. If you see here, if there is a continuous recessive bit, then automatically CAN controller will add one stuff bit, that is dominant bit. If you see here, if there is a continuous 5, the dominant bit, the sixth bit will be automatically assigned to stuff bit, and it's a recursive bit. Just opposite bit will be assigned whenever there is a continuous bits, because the bus will be synchronized, should be always because you don't know how when the bus is going some error state. To ensure there is no error, and to resynchronization technologies, to ensure that this bit stuffing is or bit streaming is involved. If you see here, 1 to 5 is transmitted, and there is a dominant bit stuffing, and 6 again it starts from here to here. This is the way to CAN is getting resynchronized with the other nodes. Even other nodes knows this is just a simple bit stuffing. It's really not required. It's not really used on the real-time data. Just it will ignore and receive this data format again, and it will give it to the user. Yeah, already I have mentioned the bus synchronization. It's a hard synchronization to start off the frame bit, and resynchronization on each recessive and dominant edges. Ensure the correct sampling up to the last bit. Every dominant bit, if you continuous recursive bit, then there will be a resynchronous. The bit stuffing will come to the point. Okay, it's a bit timing. Again, we have a four bit timing concept where there are segments where there synchronization and propagation and phase buffer and phase buffer second segment. How this is only one bit. It's not a byte. It's just a bit. That bit has a time content. It's a like a uh, the one bit time content, or one bit time has multiple time content based on the, if it is a synchronization bit, then it's a one time content, and it's a propagation time segment, then it's a 1 to 8 time content. It's like how single bit will be divided multiple segments, then based on the time content it will be transferred on the physical bus. I think most of the concept we have covered. Yeah, I think you have some few questions or open points will be there. You can post with your questions with your mail ID on the live chat. Yeah, I will revert back you what are the things, and even you can add comments once the video is uploaded on the YouTube. Even you can add your comments. I can reply all the comments to uh, and even with your mail ID, or even if I can reply on the comments publicly, then everyone can see their ways. The yeah, everyone expecting the final one. Yes, yeah, the feedback link. Yeah, this is the feedback link. You can give these your details and email IDs on this link, and you can get the certificates from the your mail ID. And yeah, maybe I'll give you some few more minutes to note down, and yeah, even I'll ping you as well the live chat. I think everyone who are participate in the session, yeah, thanks for participating it. Yeah, if you have any questions technically, or uh, yeah, even you have not only in the CAN protocol, you have any technical questions related to embedded system, you can post me on the Tamil Pudayal channel. I can revert to you, or in a video or in a test format, every anything. Yeah, might be it will be interacted from you and me. Yeah, thanks for participating, uh, who all are joining it, and thanks for Department of Tribly, sorry, Department of ECE who are conducted the session. Yeah, thank you. Thanks, guys.